Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is the IP addressing, subnetting, binary, and NAT video. And if it sounds like we've got a lot going on in this video, you're right, we do. So we're going to get to it pretty quickly here after we take a quick look at the outline for this chapter, and it pretty much contains everything that the title does. We're going to talk about some IP addressing basics, including some basic binary conversion. And I want to stop you right now if you're panicking when you hear that, because you're going to find out that binary conversions are really quite simple, and you need to know where an IP address comes from. You know, if you're looking at 217.21.21.21, where does that come from? I mean, what does that mean when we get down to the physical layer of the OSI model, when we've got to take ones and zeros and send them across the line? So we'll take a look at that, the default IP address classes, and private address ranges, where they're defined, what they are, and why we have to use them in the first place, which directly ties into a discussion of NAT and PAT, network address translation, and port address translation. Very closely related, really do the same thing with one major difference in their operation. And finally, we're going to talk about why we subnet. Because on this particular exam on Network Plus, you're not going to be given subnetting exercises to perform during the exam, but you will in certain other vendor certifications, namely the CCNA. And I mentioned that a couple times throughout the course because it's a natural progression for people to get both of those, and I think it's an excellent combination. But you need to know why we subnet in the first place, and of course what it is, and when you find that out, you'll say, oh, okay, that's pretty simple. But why we subnet is a little bit different. And we're going to get to that, like I said, at the end of this video, and then I'm going to give you a little additional information above and beyond Network Plus, because subnetting is a really important skill to have in networking. And it's really undervalued, and unfortunately there's some bad information out there. So I'm going to talk to you, not off the record, because I am speaking into a microphone, but away from the Network Plus, and give you a little professional and personal guidance when it comes to learning how to subnet. But first, before we worry about subnetting, we better worry about IP addressing basics and what's going on with this. So IP addressing is the address scheme that most of us are familiar with. This is layer 3 addressing. We talked about MAC addresses earlier. They operate at layer 2. That's what the switches are looking at. But now we're at the addressing level that we're more familiar with, and that's layer 3, the routing address or the IP address. And the reason that we spend so much more time with IP addressing really is that when it comes to security, you know, denying or permitting certain kinds of traffic filtering, other advanced networking topics, you're going to have the opportunity to use MAC addresses in some of those things, but almost all of them you're going to have the option to use IP addresses, to filter on IP addresses, to block traffic on IP addresses, to give certain traffic flows precedence over others for transmission because of their IP address. But before you even worry about any of that, let's get the basics down first. Now, an IP address is expressed in dotted decimal format, as shown here on the whiteboard, 100.111. And I mentioned in the MAC addressing chapter that you can express a MAC address in this kind of format, but it's really rare. You'll see a MAC address more with colons and dashes in an IP address. This is the only option for an IP address. You're not going to see colons between the octets, and you're not going to see dashes. And notice that I called those octets. Now, oct is the prefix that means 8, and each one of these numbers, 100, 111, those are 4 octets that we're looking at there. And they're called octets because they're actually a decimal representation of an 8-bit binary string. And even though through the magic of technology, I can see you rolling your eyes from here. Decimal, what? You know, binary string? I don't want to know binary strings. What's a binary string? Listen, hang in there with this, because you need to know some basic binary math and binary conversion skills, and you're going to be astonished at how easy this is. And I want to warn you, sometimes when you read this on paper, it can seem kind of complicated. I'm going to tell you point blank what the magic is here. You've got to practice it. And as you go on and you look at other certifications and you get into subnetting and you get into more conversions, I'm telling you, the magic key to the whole thing is practice. It's not memorization. You got to know how to do it. And I'm going to show you how to do a basic binary conversion right here. And you can practice these on your own time. You can make up your own IP addresses and convert them to a binary string and then convert the binary string back. It's all about practice. Now, why do we have to do this in the first place, though? Well, it's not just something to make the exams harder, because it's not going to be harder for you anyway. But remember from our physical layer discussion and something I say all the time in networking, it's all ones and zeros. And that's true of everything, and that's true of IP addresses as well. Particularly true of IP addresses. Because let's look at just the first octet of this address, the number 100, the decimal 100. And that's the numbering system that you and I use every day. Now the problem is we can't send 100 across a wire and have it mean anything. It's got to be a series of ones and zeros because that's the only thing we can send across the physical wire. And we can do that because the numbers are going to be in binary when they go across the wire. You know how the ads for computer schools, when you see them on TV, or other computer-related products, you'll see these strings of zeros and ones in the background, and ooh, make it look complicated, because it's computer stuff. Well, all that is a binary string. Because again, when it comes right down to it, when we're sending all this stuff across the wire, we're doing it with electrical signals. And we can only have two states, on and off. On is 1 and off is 0. That's all we have. So when we're looking at a binary octet here, or an octet, and what we're gonna do here live is convert the decimal 100 to a binary string. And all you have to do is put down this row of values. Now again, I don't mean to give you a dad lecture here, but the one thing you want to avoid as you're learning binary skills and hex skills and subnetting is doing it by memorization or trying to memorize charts or some trick or something, because you don't need any of that stuff. It's actually more complicated to try. I've seen charts, that were 80 lines long, and people say, yeah, memorize this before you take the exam. It's like, well, why would I do that when I can just learn how to do it? And you're going to see here that I went from left to right to put that on the board. But when you're starting with this, you may be a little uncertain of what the values are. And what you can do is actually write them out from right to left. Start with the number 1 and double that 7 times. Just double it. Double that is 2, double 2 is 4, double 4 is 8, and so forth. You see the pattern already. Believe me, that's the most complicated part of the whole thing. Because every single one of these values that I just put on that line are either going to have a 1 or a 0 assigned to it. It's just that simple. And again, don't worry about memorizing this line. You can just start with 1 on the right-hand side and go from right to left and keep doubling it. And all you're doing is taking whatever decimal you're given to be converted and working from right to left, from left to right, and ask yourself, can I subtract this number from the decimal remaining? And if not, you put a 0 under the binary value. And if you can subtract it, you put a 1 there. You will never have a 2 in any of these columns. Now, when you listen to me explain the process, I admit it sounds a little clumsy. But once you do it a few times, you're going to find out that it's very easy. So right now, let's take the number, the decimal 100, and convert it. And again, working from left to right, can I subtract 128 from 100? No, absolutely not. So I'm going to put a 0 there. See how hard that was? And man, it's really all you're doing. Now the question is, can I subtract 64 from 100? Well, certainly I can, and that's going to give me a remainder of 36. So I'll put a 1 there. Can I subtract 32 from the remainder of 36? Absolutely I can. It's going to give me a remainder of 4. So I'll put a 1 there. Can I subtract 16 from 4? No. Can I subtract 8 from 4? No. Trying to line that up perfectly could be a little difficult. There we go. Can I subtract 4 from 4? Absolutely, and I have no remainder. So I put a 1 there. And since I already have a remainder of 0, I'll go ahead and put zeros under the other numbers. And that right there is the foundation of anything you'll ever do with binary and subnetting and converting IP addresses, the whole bit right there. Right there. The decimal 100 is equivalent to the binary string 01100100. And that's it. That's all there is to it. And if you want to check that, all you have to do is add up the numbers that have a 1 under it. And here we have 64, 32, and 4, and that equals 100. So congratulations, that is your first decimal to binary conversion. And this skill is the foundation of performing subnetting, getting some other computer certifications when they ask you subnetting questions, conversion questions, everything you'll ever do with binary, the foundation of it is right there on that screen. That's all you do. You never panic, you learn the fundamentals, and you'll be surprised at how quickly you learn how to perform all these operations. Because when it comes to binary, just remember, there was a time in your life when you didn't know how to do decimal math either. You know, we were all at an age sometime where, 10 minus 5, how in the world do I do that? But you practiced it a few times as a kid, and you got it right. So the same thing goes with binary. It looks foreign to us because we don't use it that often, but once you dive in, you're going to be perfectly fine. Having said that, and having performed our first binary conversion, let's get to the IP address classes. Part of every IP address you see indicates what network the host is part of, and the other part is going to identify that particular host. So again, part of an IP address is the network portion, and part of it is the host portion. And one skill you must have for Network Plus is to be able to look at an IP address and determine what class it is, determine what the default mask is, determine what the network portion of the address is, and determine what the host portion of the address is. Now, a lot of books out there list only 3 network classes, but there are 5. And since you should never assign an address from the last 2 classes we'll talk about here, you better know what they are beyond the exam. You better know them for the real world. So we're looking strictly at the first octet here of each particular class, because when you can look at a first octet of an IP address and immediately tell what its class is. So with Class A, the first octet is 1 through 126. For Class B, 128 through 191. Class C, 192 through 223. Class D, 224 through 239. And then Class E, 240 to 255. Now, if you're particularly eagle-eyed, you noticed a number missing there pretty early, and that's 127. 127 is the reserved first octet for loopback addresses, such as one we talked about in an earlier video with 127001 being the loopback address assigned to a PC. So we cannot assign any address that begins with 127 to a host. You can't put it on a PC, you can't put it on a router interface or a server. You can't use that range. Now we also have 2 other ranges here we can't use, and that's Class D and Class E. The Class D range is reserved for multicasting, and those again begin with an octet from 224 to 239. Class E networks, it really depends on which document you read about the official explanation. Some of them will simply say reserved for future use. Some of them will say experimental use. I go with experimental use because that's what the IETF says, the Internet Engineering Task Force. And Class E is reserved for them. And frankly, just to do whatever they want to do, and we don't ask any questions because we got enough addresses as it is. So again, for exam and real-world purposes, let's look at the unacceptable ranges. And the unacceptable ranges, anything beginning with 127 and anything beginning with 224 through 255. It's unacceptable to have any IP address beginning with any first octet in those two ranges. Of course, one of them is not a range, it's just 127. But anything that's Class D or Class E, you can't assign that to a PC. So you should be prepared on the job or in the exam room to examine a list of IP addresses and say, okay, which one of these can we put on a host, which ones can we put on a PC or a server or a router, and which ones can we not. So that's why I want to tell you about Class D and Class E, because you can't use those. Now, what's all this got to do with identifying what the network and host portion of an address is? Class A, B, and C, those are the acceptable ranges to assign to a host. And they all have different default network masks. And it's that mask that tells you which part of the address is the network portion and which part is the host portion. And these are the default network masks. Class A's is 255.0.0.0, Class B 255.255.0.0, Class C 255.255.255.0. Now, even if you were already familiar with these default masks, you might be wondering what that business is with that, that slash and that number behind it. This is another way to express a network mask, and you may or may not see this on Network Plus, but you see it in a lot of network documentation. So for real-world success, you need to know what that is, because it's a very popular way of expressing a mask. This is called prefix notation, and it's pronounced in these three cases /8/16/24. It's much less complicated than it sounds. It's a lot easier to say than an actual mask. The number behind the slash is simply the number of consecutive ones at the beginning of the mask when it's expressed in binary. Because 255, let's look at it this way. Down here, we'll put it down here at the bottom of the screen. That's 4 octets. And it's very easy to see, where the ones end and the zeros begin. But the first octet is all ones. If you see any first octet or any octet period where all the numbers are set to 1, all the bits, you don't even have to add that up. That's 255. Excuse the red squiggly there. That's okay, because that program doesn't like that. But you can see here that is 8 consecutive ones at the beginning of the mask, so we call that a /8 mask. It's a lot easier when you're talking about network masks to say /24 than 255.255.255.0. And for those of us who don't like to type numbers, which is just about everybody in this business, I think, it's a lot easier to type. It is just easier. It's more intuitive than continually typing out network masks. Again, you may or may not see that on Network Plus, but I don't want you to be surprised if you do, and you'll definitely see it in network documentation. I wouldn't want you to walk into an exam room or a job interview room and not know what those slashes are. So again, that's simply its prefix notation, and in these three cases, it would be pronounced /8, /16, /24. You just say slash and then whatever number is behind that. So again, that's the preferred way of expressing subnet masks. Now let's get back to those network and host portions. As I mentioned in the middle of this whiteboard, what these masks mean. The Class A network mask 255.0.0.0 means that the first octet of the address is the network portion and the final 3 octets are the host portion. The Class B network mask /16 or 255.255.0.0 means the first 2 octets of the address are the network portion and the final 2 octets are the host portion. And you can already see where we're going with this. A Class C network mask means that the first 3 octets are the network portion and the last one is the host portion. When you're actually performing subnetting, you will see where this really comes in handy. I hate to just give that to you and say, hey, remember this. Because it may not seem like it's really important now, but later in your studies and as you progress on to doing subnetting, it becomes very important. So make sure for exam purposes and real world purposes that you have all this down. You know those default network masks. You know what they mean. You know where the network portion is and the host portion. And you can practice this actually on your own. Let's just take the address 23.14.189.200. For any IP address that I give you or that CompTIA gives you or an employer gives you, you should be able to do these four things immediately. You should be able to look at that and name the address class. You should be able to name the default mask. You should be able to name the network portion of the address and the host portion. A fifth thing that you should be able to do before all of those, you should be able to tell me if this is a valid address for a host or not. And this one is. It's a Class A address. It's perfectly valid. Remember, anything beginning with 227 or a first octet higher than 223 is out. Can't use them. So looking at this, we can tell, first off, with the address class, that it's Class A. And you have to know that the default mask is 255.0.0.0 or /8. The network portion then is simply the number 23. And the remaining octets, 14.189.200, that's the host portion of the address. That's actually defining the host on the network, 23.0.0.0. So very important skills to have, not just for the Network Plus exam, but for your future as well. And speaking of the future, planning for the future, you hear me in all of my courses say, you got to plan for future growth because the networks are always going to get bigger. And that's one thing we tend to forget sometimes. We don't plan for the future as well as we should. Well, one such situation kind of came up like that a while back about IP addresses. Because we thought for a long time we had plenty of IP addresses to go around. But you have to remember, we also used to think that no one would ever need to store more data than would fit on a floppy drive, right? Now you can't even buy a computer or a laptop that actually even has a floppy drive on it. So, again, we don't always plan for the future terribly well. And, of course, then networking exploded, and we started running out of IP addresses. But one thing we do in IT is react well to some kind of crisis like that. Because at the time, some companies, vendors, Cisco started pushing what we call IP version 6. This is IP version 4, by the way, when you see an address like this. And a couple years ago, they tried to really push IP version 6 because, believe me, the addresses are much more complex than this. And they pushed it kind of hard, but the world wasn't ready for it yet. And the reason it was pushed so hard is because we were running out of version 4 IP addresses. I mean, all of a sudden, every printer on every network in the world had to have a network card. Printers were networked. Everything's networked now. But kind of like we did with Y2K, but on a smaller scale. You might have heard a little something about Y2K. It was in all the newspapers. And, the world was going to end, and et cetera, et cetera. And, the IT field really did itself proud with that. And it came up with a lot of great fixes for a lot of things, and we got through it pretty much unscathed. Well, the same thing happened with the IP address shortage, because what happened was a range of private addresses was developed, and they're called RFC 1918 private addresses because the RFC stands for Request for Comment, and it's a highly technical document on RFC. If you want to see one, you can just go to your favorite search engine and type in RFC 1918, and you'll probably get the RFC that I'm talking about. You can see it's a very formal document. And this is really what saved our hash at the time, because we have the question, what is going to happen when we run out of IP addresses? And fortunately, we came up with RFC 1918 private address ranges, and that made it so we didn't have to run out of IP addresses because, see, the theory was at the time, just like with MAC addresses, that every device in the world had to have a unique IP address. Well, with MAC addressing, that's not so bad. Why? You remember why? Because we use hexadecimal, and that gives us millions and millions, and I know how I sound like, but billions and billions more MAC addresses that we could use. But IP addresses, we don't use hex, and we started running out of addresses. So we came up with RFC 1918 private address ranges. These address ranges that are on the whiteboard now are reserved for devices on internal networks. And you can say, well, internal for what? They can't be placed on devices that are going to be communicating over the internet, such as, say, a router interface, a serial zero interface. A serial interface on a router is the one that's going to be facing the internet, so to speak. That's going to be the way out of your network and to the internet. And you can't put these addresses on those, but you can put them on host devices. You can put them on PCs, you can put them on printers, put them on whatever you want. And as long as these particular devices don't have to communicate over the net, they don't have to be routed outside of your building or your network, then it's okay to reuse them. And if you've ever worked with any of these addresses, maybe you didn't know why, but you go to a school or you go to really anything, any internal network, and all of a sudden you're configuring it and you're using addresses from one of these three ranges. And that's why, because these addresses can be duplicated anywhere. As in this particular exhibit, we've got two host devices on two separate networks at two separate locations because we've got two routers at the top. That indicates a serial link, by the way, or a wide area network link when you see what looks like a lightning bolt or a jagged line between two routers. That's a wide area network link. So we've got these two hosts, and as long as they don't need internet connectivity, as long as they can do everything they need to do inside their own network, we can reuse the same IP address. And there's no problem because these two devices are never going to talk to each other, and they can't possibly meet. Because there's no problem with assigning hosts on different local area networks the same IP address if both of these criteria are met. First, they're in one of the three private address ranges, which this is Class A. And secondly, they have no need to communicate with an internet-based host. So again, it's worth repeating that any host using an address from any of these three ranges, they cannot communicate with any device on the internet. They can't go to a web server and use it. They can't do anything. If they tried, the routers in the network we just looked at, they would just discard it. The router would just discard it. It wouldn't even try to send it out because there's no way it can be routed back. It's an unroutable address. These ranges are sometimes referred to as non-routable addresses. Now, as happens so often in networking, we're solving one problem, but we're creating another one. Because when these address ranges were developed, I don't want to say the internet was in its infancy, but it certainly wasn't used to its potential the way so many businesses use it now. Schools are a good example of that. Because it used to be, say, 9 years ago when I started my career and I was working at a school, for a school, that it was easy to say, well, we'll just block internet access for the whole school because we don't want kids on the internet. Well, now, though, that's not really practical because the schools use so many web-based applications. Web-based applications are really the thing of the future, and they're also the thing of the present. Because instead of having to install software everywhere at all these PCs in the school, they're just connecting to a web server and using the web-based interface and using the software on the web server. So the problem with the RFC 1918 private addresses at this point, it's really impractical to have a network with a lot of hosts that just cannot have internet connectivity. It's not really practical. And of course, on the political side, you're always going to have somebody mad because they can't go to, play poker online or something like that. So for one reason or another, it's not really practical for us to say, okay, no one in these address ranges can get on the internet. We can grant internet access to hosts using addresses from these ranges. And we do that with network address translation, more commonly referred to as NAT. So now we know that NAT will allow a PC or a host device that's using an RFC 1918 private address to communicate successfully with an internet-based host. How exactly does that happen? Where does the translation come in? The name is definitely the recipe with network address translation. That's about as straightforward as it gets. Well, the translation is happening at a router. because a router is the only device that can successfully run NAT. Because NAT needs to be happening at the edge of your network where internet access begins. So it's not going to be on a switch. It's definitely not going to be on a hub or a repeater. It's going to be on a router. And when I refer to a NAT router, I simply mean a router running network address translation, not a router specifically built for NAT, because most higher level routers and even mid-level routers can run network address translation. Now, a router configured to use NAT is going to translate the private address of that host, the PC we see there at 10.1.1.2, to a routable address so it can communicate with a web server located at 210.1.1.2. Now, the great thing is that when the web server sends files back destined for that translated address, the router will get them and then translate that address back to 10.1.1.2 and route them normally. And the only device that even knows this is going on is the NAT router itself. The entire process is absolutely, totally transparent to both the host and the web server. We don't have to go to the host and configure it for NAT. The only device that needs to know about NAT is the router. Now, I know that NAT theory can sound a little chunky, a little thick when you just hear it, so we're going to go through this step by step, and you'll see where the translations take place and what they would be. First thing to keep in mind is that even when we configure this router for NAT, it does not mean that every host on the inside network, on the private network, is going to be eligible to have its address translated and have internet access. If this were the only host on the entire network that should have its address translated, we can configure it that way. That's not a problem. We determine which addresses or which hosts will have their addresses translated. Now, in the example we're going to look at here, the host is going to send a packet destined for the website. And we're going to walk through the steps that would occur in that network. The first question the router is going to ask itself is, should I perform this translation? And if so, what should I translate the address to? Now, the packet is coming in with a source IP of 10.1.1.2 and a destination IP of 210.1.1.2. The router knows that's an RFC 1918 private address. If we configure NAT to translate that address and to allow that host internet access, we also have to name what address it should be translated to. Now, we can define an address or a pool of addresses similar to DHCP, but the router then looks at its configuration, says, okay, I should perform NAT on this, and I should translate the source address to 180.1.1.2. And when the packet leaves the router, the destination IP is going to be unchanged, but the source IP address has been translated from 10.1.1.2 to 180.1.1.2. Now, what's going to happen also is that the router keeps what we call a NAT mapping table. And it's going to say, okay, I mapped or translated the address 10.1.1.2 to the address 180.1.1.2. And then when packets come back in destined for that private host, then that mapping table will come into play. Because what's going to happen is now the website is going to respond with packets. So at this point, with the arrows coming back in, the packets are returning, and they have a source IP address of 210.1.1.2. That's not any problem. The destination IP, though, is 180.1.1.2. And the NAT router is going to look at that destination IP and say, okay, wait a minute, I'm going to check my NAT mapping table because I know I mapped that address to a private address. And the router looks in the NAT mapping table, sees that 180.1.1.2 was mapped to 10.1.1.2, and translates the address accordingly. So you can see that when the packet leaves the NAT router, the source IP address is unchanged, but the destination IP address has been translated back. And again, all this is transparent to the internet-based host, the web server, and it's transparent to the private host. Really works well too. I've configured NAT and used NAT for years, and it is one sweet protocol. And this is how we got around the problem of running out of IP addresses with private addresses, and then of course NAT allows us to get private addresses out onto the net. A couple of NAT notes for you. Again, as I mentioned, I think twice during this particular lecture, the entire process is transparent to all devices except the NAT router. The public addresses used for NAT have to belong to your organization. You have to have bought those. You don't just get to pull IP addresses out of the sky and use them for NAT. There is a static NAT and a dynamic NAT configuration. The configurations of those are way beyond the scope of Network Plus. But just to give you a little additional information, static NAT is a one-to-one mapping. You actually sit down and configure, okay, this address gets translated to this address. The problem is, of course, you're tying up addresses that may not be in use. So dynamic NAT kind of works like DHCP. It keeps a pool of routable addresses, and it's frankly first come, first serve. If you've got 200 PCs on the inside, and they're trying to get out to the net, and there are only 5 addresses in the pool, the first 5 to get the addresses are in good shape, and the other ones are not. And again, just as a reminder, switches, hubs, and repeaters cannot run NAT. Only routers can run network address translation. Having worked with NAT for, frankly, years, I can tell you that it's actually pretty simple to configure, and once you have it up and running properly, it just works beautifully. You never have to go back and continually tweak it. And once you've got it running and you've got the users getting out to the net who should be getting there, there's one drawback to NAT, though, that it assumes that you've got extra routable addresses that you have purchased but are not using. And for some smaller networks, and especially some of the schools I've worked with, that's a faulty assumption. Because when a school system buys routable addresses from an ISP, they're not going to buy them just to have them sitting around. They're going to buy as few as they need, but they're not going to have extra ones just sitting around waiting to use with NAT. So that is where port address translation comes in. Port address translation allows a network to use a single routable address to allow multiple hosts to access the internet. Now that sounds good enough as it is, right? I mean, you're taking one address and you can allow, 10, 15, 20 internal hosts to access the net. But even better, that single routable address can be the address that's already in use on the router's serial interface facing the internet. So not only do you get to have multiple internal users go out to the net on a single IP address, then you've also already got that IP address doing double duty, really. It's already in use as the IP address on a serial interface on the router. Now, at this point, you're probably thinking, okay, Chris, you've really lost it. How in the world can that happen? Well, let's take a look, and when you take a look, you'll see why we sometimes refer to PAT as overloading. Here's an illustration of how PAT actually operates. And what we've got is a router with an IP address of 180.112 on the serial 0 interface where these packets are going to be leaving. So address 180.112 is already in use, but PAT is going to also allow us to use it to perform address translation and allow different hosts with private addresses to access internet-based hosts using a single routable address. Now, it's the same format as we looked at with NAT. You can see on the left-hand side that we've got packets coming from 2 different source IP addresses, 10.112 and 10.115, and they're sending packets to 2 different destinations, 210.112 and 210.117. Again, this router already is using the IP address 180.112 as the address on the serial interface on this router. That's the interface the packets will be leaving the router on to reach the internet. Now notice that the source IP address of the packets leaving the router is the same, 180.112, but the port numbers are different. The packets from 10.112 have been translated to the IP address 180.112 port 2043, and the packets from 10.115 have been translated to 180.112 port 1928. And again, the router is going to keep a mapping table just like it did for NAT. And when the packets come back from their respective destinations, when those destination IP addresses respond, the IP address port number combination will be examined by the PAT router, and the address is changed back to the proper IP address. So the operation is really just like that of NAT, except that we're involving port numbers. That's why we call it port address translation instead of network address translation. Now again, PAT is often referred to as overloading. It's actually very rarely referred to as PAT, as a matter of fact. There are two reasons for that. First off, we are overloading an IP address, in effect. But the other reason is that the actual command that differentiates NAT from PAT on most routers, including Cisco routers, is the simple word overload. The configuration is going to look exactly the same, except the word overload is going to be at the end of one of the commands. And that's what changes NAT into PAT. And it works beautifully, really does work nicely. So that's what PAT does for us. Now we're going to talk about why we subnet. And the actual procedure of subnetting is not in the scope of the Network Plus exam. And I'm going to urge you to learn it, whether you pursue a certification that does make you learn it. Say the CCNA, it's very big on subnetting. And I'm going to tell you, when you learn subnetting, and this is just a little dad lecture here, a little lecture on the side. Actually, that's how I got started in teaching, is teaching people binary and teaching them how to subnet. That's actually why I got into this field. I got tired of seeing otherwise very bright people who couldn't subnet, and it wasn't their fault they couldn't subnet. It wasn't their fault they couldn't use binary properly. They just hadn't been shown how, because so many of the books and so many of the videos out there would have you memorize these charts that were just unwieldy. And when you memorize something, you're not really learning it. And I would have people come in for job interviews who were CCNAs and CCNPs, and they couldn't subnet. They literally could not do it because they had memorized a chart. And back then, and this was 6-7 years ago, memorizing that stuff was enough to get a CCNA. Well, it's not anymore, and it's certainly not enough to be good at it in the real world. So don't let anybody tell you, oh, just memorize this chart for subnetting and you'll be fine, because that's not what you want to do in a professional field. Let's remember back to junior high school when you memorized something for world history class. Did you remember it a week later? No, because you probably don't have to use it again. But subnetting is something you need to know to be a world-class network troubleshooter, to be a networking engineer, to be a world-class network admin. So again, it's out of the scope of the Network Plus exam, but I urge you to learn it. And when you do learn it, when you learn binary, when you learn subnetting, really learn it, because I've literally had thousands of people around the world tell me, why didn't someone else just say this? It's pretty simple. Don't be fooled by the charts. Don't be fooled by the tricks. Just learn how to do it, because frankly, it's just not that hard. And thus endeth the lecture for today. Now let's get back to why we're subnetting in the first place. Why are we doing this? Well, subnetting itself is the process of taking a large block of IP addresses and dividing it into smaller blocks. That's all you're doing. When a company, we talked about a company or a school purchasing routable addresses. And when you do that, you're not going to be given an entire huge range of addresses unless you're willing to pay a lot of money for them. You're going to be given just enough addresses to get the job done. And that small subset of IP addresses, it's called a subnet. For example, I purchase IP addresses from an internet service provider to put on Cisco routers here at my home office location, which allows my CCNA and CCNP students to connect to them remotely and work on the real thing. Now, when I buy those addresses, they're going to sell me a block of them. The ISP is not going to say, sure, Chris, here's a block of 300 addresses. They're not going to do that. For one thing, I don't need that many, so it's a waste of addressing. And secondly, I don't want to pay for them, because the more addresses you get, the more you have to pay. So the ISP basically just cuts a little block of IP addresses off and gives me that block. It's really, you know what subnetting is? It's really like taking a pie and cutting it into smaller slices. And with subnetting, you're just taking a larger network number and segmenting it into smaller logical networks. Subnetting has quite a few benefits. This is why it's so popular. First, routing is by far more efficient. And as you progress in your routing studies, you will definitely see what I mean. Your routing is much more efficient when we have multiple smaller subnets rather than just one big network. And that also helps cut down on broadcasts, as you'll see. Now, subnetting, again, it saves bandwidth because the broadcast scope is reduced. And it really optimizes your IP addressing scheme by lessening the number of wasted IP addresses. Let's take a point-to-point connection. And by rule, you know, how many IP addresses could I possibly need for a point-to-point connection? Let's take a look at one. Here's a point-to-point network, a point-to-point connection between two routers. And again, when you see what looks like a lightning bolt or a jagged line between two routers, that's indicating a serial line. So this is a wide area network most likely. And again, how many IP addresses do we need here on that point-to-point network? We only need two, right? One for each end of the connection. By rule, I mean, a point-to-point network is just that. We only need two. So if your internet service provider can only sell you a block of 254 addresses, you'd be wasting a lot of money and they'd be wasting a lot of addresses. So what the ISP does is they subnet. And again, all we're doing with subnetting is taking one large block of addresses and dividing it into subnets. And you'll notice here that the slices of my pie, my network pie, if you will, are not the same size. The subnets you work with when you begin studying subnetting are pretty much going to be the same size, but as you get into more advanced studies, you'll realize that subnets are not all going to be the same size in a network. And it's just like I said with the previous network, we would only need two addresses to make that work because we've only got two possible hosts there. So again, your ISP can subnet that and sell you literally only two addresses, and while they still have 252 of the original 254 addresses. They're not doing that to be nice to you. They're doing it because they're going to sell them to somebody else. And by the way, a term that can, causes a little bit of confusion, CIDR, classless interdomain routing. All that is subnetting and what we call route summarization done by your ISP. That's all there is to it. You'll find that subnetting and CIDR are really much alike. So if down the road someone says, well, we're going to perform some CIDR here, or learning that's really hard, it's not really hard. All it is subnetting. So again, I urge you to learn more about subnetting when you're done with your Network Plus studies. Like several other things here, like security protocols, we're really just taking an overview and looking at the basics. You're going to need to know how to subnet and work with subnets to earn other vendor certifications such as the CCNA or Microsoft certification. But I'll tell you, once you learn subnetting, it's a huge step forward in your own career, because that's one of the first things that I've ever looked at in all the job interviews that I have done over the years is ask someone to subnet. And it is amazing the correlation between people who could subnet. They really tended to know what was going on a network. And people who just didn't have any idea had basically just memorized a lot of stuff but couldn't put it into action. So it does help separate you from your competition for better jobs and more money. So that's about it for this part of the video, though. But let's take a little bit of a review here, because there's, again, a lot of information. Some of this totally new to some of you with the IP addresses and address ranges, that kind of thing. So let's take a quick review of what we've looked at here in this video. As we take a look here at the high points of this particular video, I really want to stress to you that this video, as far as I'm concerned, is really the most important in this course, not just for Network Plus. I'm not saying they're going to ask you, most of your questions out of this section, because that's not true. But as far as Network Plus exam goes, as far as future certification exams go, as far as real-world networking success, this really is the most important chapter, because we work with IP addressing all the time. And a lot of us work with subnetting on a regular basis. Most real-world networks right now use network address translation. And as IP version 6 comes into play more and more, maybe NAT will be de-emphasized. I'm sure it will eventually, but that time is a ways off. So there's a lot of real-world experience that you can gather from this video, then finding out, how NAT is used at your office. If you're not the person in charge of that, ask somebody who is, because you really want to find out as much as you can about it, because it's great for certification exams from other vendors, and it's great to know for real-world networking success. Because IP addressing, I mean, hey, it's going to be on every network you ever work on, right? I mean, we got to have IP addresses. We're going to have subnets more than likely. You just don't see many networks today that do not use subnetting. So when you see those subnet masks, you need to know what they mean. And as far as the Network Plus exam goes, they're not going to ask you to perform a lot of subnetting, but other vendors will. Cisco is very heavy on that. And you don't want to let that intimidate you, and it all really begins with the basics. It begins with the fundamentals, and that's why I put on here, to learn how to convert decimal to binary and vice versa, you got to practice it. Because when you practice it, it's like anything else, like driving a car, it's like riding a bike. First time you did it, you were pretty nervous, right? Your arms are all tense, and you're thinking too much. Well, that really happens in my in-person classes when I get to the binary math lecture. I always kind of chuckle to myself inwardly, because there will always be a couple of people in the class who look like they've just been strapped into the electric chair. Their arms are really tense, and they're grabbing that chair, and it's, oh no, I don't know binary math, and this is going to be horrible. Well, it sounds intimidating, and not that many of us get to use it on a daily basis, but once you start practicing it, you're going to be amazed at how quickly you can do the basic conversions, and once you master those, you can do the intermediate and then the advanced questions that other vendors will ask you. So again, I would say, if you've got 5 minutes at work or, at home, anything like that, get some practice in. And you don't have to buy a certification exam, a practice exam, to practice your decimal and binary conversions. You can just write a random number out. 237. If I was given the number 237, what would that be in a binary string? That kind of thing. So just take a few minutes here and a few minutes there, do a few extra conversions. Just sit down and just randomly write out a binary string and say, okay, what would that be in decimal format? And I'm telling you, that little bit of practice here and there will serve you very, very well in the exam room and in the real world. So that's the end of my subnetting lecture there. And, let's get over to the first octets of these particular address classes. Good stuff to know for the exam and the real world. And I went ahead and put A, B, C, D, E there just to remind you what Class D's and Class E ranges are. And remember, Class D and Class E, those addresses are not appropriate to put onto a host device. Class D is reserved for multicasting. Class E reserved for future use or experimental, depending on which documentation you read. A, B, and C, you should be able to look at an address, an IP address, and immediately say, okay, I know this is Class A, or I know this is Class B. You should know those default network masks as well, and keep in mind that 127 doesn't belong to any of these because that is reserved for loopback addressing. Here are the private address ranges, and again, this is what I mean by other certification exams as well, asking you about IP addressing. You should be able to look at an address immediately and say, okay, I know that this is a private address. I know that we can put it on a host in a private network, in an inside network, if you will, but if we want this person or this host to be able to communicate with an internet-based host, we've got to use NAT. The one thing I do really want to point out, and this tends to trip people up who are just learning this, so I really want to point this out for you if this is totally new to you. Please note that the masks that are used for Class A, B, and C private addresses are not the default masks. And let's take a look at that. You see here with Class A what the default mask is. There's Class B's and there's Class C's. Now, Class A's is the same. Let's see if I can highlight that. Yep, Class A's mask is the same as the default class mask, but Class B is not. It's 255.240.00, and Class C is 255.255.00. So watch that on the exam and in the real world, of course. And finally, we went through a NAT example. I won't go through that again, but I really suggest you watch that so you know what's going on with network address translation. Network address translation and its cousin port address translation, they are both used to allow hosts with 1918 private addresses to communicate with internet-based hosts. And then finally, we don't really do a lot of subnetting or any actual subnetting here in this course. Those of you with your eye on the CCNA down the road, you'll definitely be bumping into a lot of subnetting. And I'll give you a very short DAV lecture here. It's a very valuable skill to have. If anyone tells you you can learn to subnet by memorizing a chart, they are wrong. And you don't want to go that route, because one day you'll be interviewing for a job with somebody like, say, me, and you don't want to be doing that. Let me see if I can remember the chart that I looked at 7 months ago thing, because I can guarantee you, you're not going to remember it. It's not going to do you any good. There. As far as the subnetting benefits go, why do we do it in the first place? There really are quite a few reasons, but here are the basic ones. Routing is more efficient to begin with, because if you're using just a giant network, or the network number that the ISP gives you, the routing is not going to be as efficient as it is if you cut it into smaller pieces. It does become more efficient. So again, subnetting, when we're using smaller networks, is a lot more efficient than routing with just one large network number. That in turn reduces the range of network broadcasts, because when a host in one particular subnet sends out a broadcast, there's a 99% chance that hosts in other subnets are never going to hear it. There's always an exception. That's why I say 99%. But the odds are they're not going to hear it. So that helps reduce the range of network broadcasts, and we're always interested in that, because we don't want broadcasts taking up the CPU of the host, and more importantly, we don't want it taking up our bandwidth. And it also helps to optimize our IP addressing scheme. We spoke briefly about a situation with a point-to-point network where literally I only need 2 IP addresses. So let's say that the ISP gave me, I buy 254 network addresses. Well, I don't want to just use 2 of those addresses and then not be able to use the others. But without subnetting, I couldn't do that. But subnetting allows me really, again, to cut a very small slice of a pie out. It allows me to carve 2 addresses away from that and use those for a point-to-point network, and then I can still use all my other addresses. So again, the more you learn about subnetting, really the more valuable you are in a network. Because as addresses get more and more cramped in your network, so to speak, as you continue to add hosts, you're going to need to know how to subnet. And really, that wraps this particular video up. I thank you for your attention here. I know, especially if this is the first time you've seen this material, there's a lot here, obviously. But again, I want to remind you, when you get back to those IP addressing basics, when you're talking about binary conversions and binary to decimal, decimal to binary, don't let that throw you. It's not hard. It should be very easy points for you on any exam. But the key is you've got to practice it. You don't want to try to memorize a chart or something like that and then walk in the exam room and try to remember it, because it just doesn't work well. And besides, to do the job, you got to know how to do the job, right? So I'm going to leave you right there with the subnetting benefits. I thank you for your time, and I'll see you on the next video.